welcome again to the course on physics of renewable energy systems. In the previous class, we discussed about the fabrication processes to obtain solar cells, and in today's lecture we will start our discussions on the characterization techniques or processes which are used to understand the functioning of solar cells, and I will also like to give certain idea to you all about the future direction which the research in this area or the development in this area will move. So, let us start our lecture today. So, in today's class, these are the concepts which we will cover. I will talk to you about the mathematical formulations which are used to characterize solar cells. We will talk to you about the types of solar cells which can be classified based on the materials that are used to obtain them, and also the future direction in which this field is actually expected to move. And the key points which you will understand after attending today's lecture would be the various processes or steps involved to calculate the parameters that are relevant to solar cells, what are the types of solar cells, and the future of solar cell technology. So, in the previous class we have seen the fabrication of a typical silicon based p-n junction solar cell, where you have a p-type layer, an n-type layer, and then you have the fingers which are fabricated on the top using the technique of screen printing. We have also talked to you about the process by which you can calculate the resistance of the whole surface or the layer which you are coating on top of it, which is of the conductive nature. And depending upon the thickness of the layer, you will have the generation of charge carriers. So, when we were discussing about the formation of a p-n junction, we had talked to you about two concepts: the formation of the drift current and the origin of diffusion current. Drift current is associated with minority charge carriers, whereas diffusion current is associated with majority charge carriers. So, diffusion current is associated with the charges that flow across the junction, whereas the drift current is associated with the minority charge carriers which are obtained due to thermal energy. Now, if I have a junction and I illuminate it with a solar radiation, I will obtain I photo, which is also the photo current, due to the electron hole pairs generated by incident photons which have higher energy than the band gap. So, you can calculate the net current, which is equal to I diffusion minus I drift minus I photo. Knowing the values of I diffusion and I drift, which was written in the earlier lectures, we can write I net is equal to I 0 e raised to the power of E v by k T minus 1 minus I photo. Now, we know that a solar cell is conventionally considered to be a battery that delivers a current equals to I cell. This current flows through the external load and it becomes more positive as I photo increases. Therefore, you can write I cell is equal to minus of I net, and if that is the case which we use, I will obtain the I cell value which is equal to I photo minus I 0 multiplied by e raised to the power of EV by KT minus 1 bracket, where V is now the voltage output of the solar cell and I cell and V are both positive. And just a quick reminder what we are doing, we are actually trying to understand the operation of a PN junction, and using the first quadrant calculation that is used to determine the value of current, we know that the current in the first quadrant is given by I equals to IL, that is load current, minus I 0 exponential QV by NKT minus 1, where N is the ideality factor. So, what happens? Let us draw a I cell versus voltage curve. You find that the shaded area is the quadrant in which the cell generates the electrical power. So, you are working in the area, the quadrant in which the cell generates electrical power. As the illumination of the cell increases, the I cell minus V curve moves upward as indicated by the dashed line. So, you have more current being obtained due to the illumination of the cell, and that is what is expected from a solar cell. So, the equivalent circuit for the solar cell can be drawn. What are we trying to draw? We are trying to actually reduce the complete device into certain electrical components. So, we have flow of photocurrent, the diode. Which diode are we talking about? The PN junction that is falling, and then a load. If there is no load, what will happen? You will get what kind of current? You will get the short circuit current if you connect the wire through. So, considering I is equal to I 0 e raised to power EV by KT minus 1, and knowing the relation that I cell is equal to I photo minus I, and if V is equal to 0, the cell current flowing in the external circuit is I photo. So, there is voltage across the diode is 0, then the cell current flowing in the external circuit will be equal to I photo, because there will be no current flowing in this direction, and then the I photo will become available to the load. So, if you substitute I photo as I short circuit current, then you get I cell is equal to I short circuit current minus I 0 into e raised to the power of EV by KT minus 1, and this gives you the solar cell equation and also gives you the mathematical formulations to determine the current which will be flowing through the cell. So, before you start characterizing the solar cell, you must find out what is the short circuit current and the open circuit voltage. Let us now see what is the maximum power which can be delivered by a solar cell. From the open circuit condition, we have I cell is equal to 0. So, we obtained that ISC by I0 plus 1 is equal to e raised to the power of e VOC by kT, because we have the open circuit and we get the open circuit voltage. Now, generally the short circuit current is much larger than the initial current, the I0, and therefore, VOC is approximately equal to kT by E ln of ISC by I0, and the power delivered by the cell is equal to the product of the cell current, that is I cell, and the cell voltage V. We have already estimated the value of I cell. So, substituting the value of I cell, you can get that power is equal to V into ISC minus voltage I0 into e raised to the power of V by kT minus 1. So, this is the maximum power which you get from the cell. So, there are two things which you will see. You have PMP and VMP. What is the meaning? The values of current and voltage that together provide the maximum power are called as IMP and VMP. So, these are the two values which are used to obtain the maximum power. We can look into the same thing once again. So, the maximum power is dP by dV, and if you use the initial formulation which we had started using the short circuit current and the I photo and I cell, you will find that as EV by kT is much greater than 1, you can reduce this equation to the form that ISC minus I0 e raised to our EV by kT into 1 plus EV by kT. Now, you can substitute in this formulation the value of short circuit current which was derived earlier, and if you do so, then you get equation number 3. So, I now have a relationship between the short circuit current in terms of I0. Let us rearrange, and if we can rearrange, you will get that the value of VMP is equal to V0, that is the open circuit voltage, with reduced by a factor kT by E ln 1 plus E by kT. And the final result is that VMP is approximately equal to VOC minus kT by E ln 1 plus E VOC by kT. So, this is the value where you have replaced V by VOC, and that gives you the maximum power that can be delivered from a solar cell. This was the process by which you determine the value of VMP, and similarly we can also derive the value of IMP, that is the current value which has to be used to obtain the maximum power from a solar cell, and that is equal to ISC into 1 minus kT by E VMP. So, the ratio of the maximum power PMP and the product ISC and VOC is called the fill factor, and it is given as PMP by ISC by VOC and denoted by FF. This is equal to IMP into VMP divided by ISC by VOC. In practice, the fill factors are approximately 80% because of physical restrictions in the design. In comparison to the fill factor, the ratio of maximum electrical power to the incident solar power actually defines the power conversion efficiency, which is given as PMP by PS, and that is equal to FF into ISC VOC divided by PS. So, these are the two terms which are routinely used to explain the parameters associated with a solar cell. For commercial solar cells which are available in the market, the efficiencies are approximately 20% plus minus, and generally the efficiencies which are reported are under the conditions of AM 1.5 and temperature of 25 degrees and power of 100 milliwatt per centimeter square. So, how do we characterize a solar cell? We again can characterize these solar cells. Now, if I have to obtain the values of ISC, or VOC under different energies, under different radiation conditions, then I use a solar simulator where I can change the intensity, I can change the time for which the radiation is available, and I can change various factors, and then I can find out the parameters which are going to change in a given solar cell. So, either you can characterize these solar cells under continuous or steady state mode, or you can also have pulsed simulators, that you have appearance of radiation and as pulses. So, for sometimes they are there, then you switch off, then you switch on, then you switch off, and then you see how the cells are responding. And this is what a typical solar simulator from Newport looks like. Let us see a few more recent types of solar cells which are being mentioned just to show that although you have new generation of solar cells, but the characterization and the mathematical formulations which are used to explain the operation of these solar cells, they remain the same. So, the first one was given by Michael Gretzel, and that was the dye sensitized solar cells, where the Gretzel group actually tried to mimic the nature, and it was reported in 1991, and if you look into the kind of citations they have, it is more than 30,000 people have actually referred to this paper in their own publication. So, it brought a new generation of solar cells into reality. So, what do they do here? They actually use a dye and which is on top of a semiconductor, and then they have the electrodes, and on illumination of light which crosses the transparent layer, you have the drop of electron to the semiconductor, and then you have the condition where the higher level is populated. So, when you have the electrons in the semiconductors which can take part in the conduction mechanisms, and the whole process is actually facilitated by using redox based electrolytes. So, this was a typical dye sensitized solar cell, and there are a lot of reports which have been coming out in literature, and very recently we have seen that the top efficiencies in dye sensitized solar cells have reached to approximately 14%. But they have some major limitations which have to be countered before they become available for large scale use. And the first one is how to ensure their stability over long time duration. Along with that, you also have to ensure that they can be operated in different temperature zones. So, you have to find ways to make these DSSCs to work for long durations as well as in varying temperature conditions. Now, as you change the conditions, although the degradation of the active material may be low, but then comes the problem of degradation of the liquid electrolytes. So, a lot of work needs to be done on understanding the processes by which you can control the degradation of liquid electrolytes, which take part in the redox mechanisms that lead to electron transfer. Still, you have to standardize processes by which you can actually make fully automated lines to obtain the cells. So, lot of work still needs to be performed before DSSCs becomes a reality. Similarly, we have the discovery of perovskite based solar cells. And what are these solar cells? These perovskite solar cells are the ones which use materials which have a perovskite structure. And if you just want to know the history of this word perovskite, it actually came in after the Russian mineralogist Perovsky, and what it happened that the mineralogists, they actually studied the structure of calcium titanium oxide, and you have a structure which is called as ABX3. So, what happens in this structure? The A type organic or inorganic cations, they occupy the cube edges. The B type inorganic cation occupies the body center, whereas the X halides, they occupy the face centers. In conventional perovskites, it was called as ABO3, but the perovskites which we are using in our solar cells, these are ABX3 types of cells. And you see this structure which is there, it forms an octahedra. So, it is called an X halide octahedra here. Otherwise, conventionally it was called an oxygen octahedra. So, you had an octahedra in where the inorganic cation was sitting at the center. So, let us see how does it look. So, you had a unit cell, then you arrange this unit cell in a lattice at the cube edges, or in this edges of these octahedra, you have the atoms, where the black atom is your M plus, the yellow atoms which we are showing in this slide are representing the lead atoms, and the small dots which at the corners of these octahedra are your X halides. So, you can choose different types of organic or inorganic ions, and whereas X atoms are either bromide or chloride or iodide. So, these are the typical anions or cations which we are using to fabricate these perovskite structures. And the first article actually came in 1893. And in today's area, we have been using, let us say, methyl ammonium lead bromide or iodides, which can be fabricated using a simple mortar pestle based synthesis protocols. So, you can use the precursors on a mortar pestle and then make a solid solution out of these precursors. The advantage of these perovskite solar cells are that they have allowed an area which is much larger than silicon cells to absorb the wavelengths, and the relative spectral response is also quite high compared to the amorphous silicon or silicon based technologies which are being used. And already we have perovskite based solar cells which are reporting efficiencies of 22 to 25%. They are easy to fabricate, they are easy to understand, and they are also easy to obtain in large scale. Along with that, they have large shelf life, and the synthesis protocols to obtain the solar cells are also much simpler, and therefore, these perovskite based solar cells are expected to bring in significant cost reduction in the whole solar cell technology. These solar cells have large scale applications. They are already being proposed for application in X-ray detectors, in devices where luminescence is occurring, or places where you want to initiate water splitting, or you can also have resistive switching based devices where these systems can become useful. And just like silicon based solar cells, these cells can also be fabricated in various configurations. These include planar configurations or meso configurations. These meso configurations, they use mesoporous nanoparticles in combination with perovskite based materials to perform the photon induced generation of charges. And if you see the literature, then let us say from 2004 to 2019, you have seen a steady growth in the efficiencies which you have obtained. And as of 2019, we are talking about an efficiency of 25%. And you can see that the earlier technologies, they could reach these values of efficiencies after a research of more than 100 years or so, whereas perovskite based research, when it has really taken off, it could reach these values in few decades or so, and that is why these are being considered as the future of solar technologies. These are the references which were used to obtain the data which were presented in today's lecture, and I hope that you have understood the process of evaluation of a solar cell. What are the parameters that are used to compare the solar cell performance, and also what is the importance of materials development in obtaining next generation solar cells. I Thank you for attending today's lecture, and from next lecture onwards we will move towards other kind of solar based devices. Thank you very much.